Nurowski for theoretical physics will talk us about this. It is not group G2. I thought that you will talk about your favorite group. So today it will be about group E6. Let's begin.
Thank you very much. I am happy to be again at this seminar. Can you hear me? I don't know. Okay, anyhow, I'm very happy to be here again. Today I want to tell you something about exceptional simple Lie groups and Lie algebras. And actually, I want to tell you something about the lowest dimensions in which these Lie groups can be realized. And actually, the lowest dimensions in which real forms of these groups can be realized. And I think that there is nothing new in my talk. It is of rather educational nature. I want to sell you a few tricks that mathematicians have to visualize how to realize these simple Lie groups in particular dimensions. So let me start. I start from this, that I would say that one of the most spectacular achievements of algebra and perhaps of the whole mathematics is the classification of simple Lie groups. This is a result of Wilhelm Killing, which he published in 1887. So in 1887, Killing published a paper in which he classified simple Lie groups. And interesting for Polish people is that at that time he was a rector of Liceum Hosianum in Braniewo, in Warmia. So he was for 10 years the rector of Liceum Hosianum, which is now Uniwersytet Warmińsko-Mazurski, I believe. It started from this Liceum Hosianum, which was actually, it was on Warmia, and Warmia is some enclave in Eastern Prussia. So it is this Catholic enclave in the Eastern Prussia, and there was this Catholic school which was called Liceum Hosianum, and Killing was rector of this school. And while being rector of this school, he made this classification of simple Lie algebras. So what Killing has established is the list of pairwise in non-equivalent simple Lie algebras, and let me spell them out. So first we have the classical simple Lie algebras, which are AL, BL, CL, DL, which could be, this classification is over C. So then these AL are essentially SLs, BLs and DLs are SOs, and CLs are SPL. And what is nice about these algebras, that all of them correspond to Lie groups preserving multilinear and actually bilinear forms in Rn or Cn. Okay, so that's what they are, and there are infinitely many of them. They are grouped in infinite series parameterized by the Lie theoretic invariant number L, called the rank of the simple Lie algebra. So these are this series of simple Lie algebras, and actually at that time, at time of Killing, I think that only Lie and Engel knew something about these SP guys. So Engel and Lie knew that there is SP3, and it's known from the letter of Killing because Killing wrote letters to various mathematicians asking them what do they know about these simple Lie groups. And in particular, Engel wrote to him that there is one more than this AL, BL, DL, which is this SP3, I would call them. And so Engel knew about SP3, and then Killing, of course, understood that there is a series of them. But the biggest discovery of Killing is that there are, apart from this infinite series, there are 5 more, and they are precisely 5 of them. They are called E8, E7, E6, F4, G2. Here are dimensions of those, right? And he understood that these algebras are possible from his classification, but he didn't Killing didn't have realization of them. Actually, he did discover root diagram for G2, and he discovered, but he did not obtain realizations of these Lie algebras, neither algebras nor groups. In particular, Killing did not obtain a realization of the smallest exceptional simple Lie algebra G2, but he claimed in 1887.
Realization, you mean?
Yeah, realization, because okay, I will distinguish between representation and realization. Representation, it will be clear soon what I mean, but for me, realization is just, I would like to anyhow visualize this group, for example, as a transformation group on a manifold, right? Which is nonlinear action. So that's, I will make a distinction between realizations and representation in a second, okay? So anyhow, but Killing somehow claimed that this group, G2, should be realized in dimension 5, right? So why dimension 5? So the simplest way of realizing a Lie group geometrically is to provide a space which is G homogeneous. Then the group is the symmetry group of the space M, and in particular, it is a symmetry of the entire structure with which M is naturally equipped. Such space is always locally equivalent to one of the coset spaces G mod P, where P is some Lie subgroup of G. Okay, so if you just look at the dimension of the homogeneous space, which is always of the form G mod P, then dimension of this space is just dimension of G, negative dimension of P. So to find realization of G in the lowest dimension, one has to take a subgroup P in G of the largest dimension. So in particular, Killing's remark about G2 being realized, that should be realized in 5 dimensions, means that Killing knew that in this G2, there is a 9-dimensional subgroup. G2 has dimension 14. Remember, I put you the dimensions: 248, 133, 78, 52, and 14, right? So the lowest one is G2. Okay, so that's about G2. And now, due to Elie Cartan PhD thesis, so Cartan at the age 24 wrote a PhD thesis in which he re-examined everything what Killing did, and he just cleaned up all the gaps in Killing's thing, and in particular, he found all lowest dimensional irreducible representations and also lowest. And he indicated what could be lowest dimensions of realizations of these groups. So now, due to Elie Cartan, we know that the group G2 has 2 geometrically different realizations as transformation groups in dimension 5. And I discussed this story, as Jacek said, many times, and also on this seminar. So today I want to discuss lowest possible realizations of the other exceptionals. As you will see, I will focus on E6. Okay, E6.
So did he consider algebra defined by vector fields, or he just
no, okay. He made all the algebraic part, meaning algebraic. So it was Killing who discovered this, what is called root systems. So he found an algebraic way of classifying the algebras. Okay, simple the algebra. But if you open Cartan's paper from 1893, which is not 1894, so before his thesis, in which he claims about, in which he summarizes what he did in the thesis. If you read what he writes there about Killing, I think that Ian Anderson says that Killing, Cartan wouldn't be invited to the birthday party of Killing because it is not nice things he writes about Killing them. Okay. So now I am coming back to this what Jacek was asking, with the exception of general relativist physicists, when thinking about realizations of the groups, have in mind their representations, and which I would call linear realizations. Cartan, in his thesis, established what are the dimensions for the lowest dimensional irreducible and faithful representation of the exceptional. So this is what Cartan in particular did in his thesis. So Cartan found the lowest dimensional representations of each simple Lie algebras, in particular, including all the exceptionals. So what he has shown is that the lowest dimensional irreducible representations of G2 is in dimension 7. And you remember that Killing said that realization, the lowest that he can realize in dimension 5. So actually these realizations which are non-linear could be on lower dimensional space. So what Cartan established in his thesis is that G2 has irreducible faithful representation in dimension 7, F4 in dimension 26, E6 in dimension 27, E7 in dimension 56, and unfortunately E8 only has this how do you call it, this adjoint representation, which is just in the dimension of E8 itself. Okay, so these are just like, so if you want to realize G2 linearly, as you have to go faithfully to, you have to go to dimension 7, F4 26, E6 27. And as I said, however, these are not the lowest dimensional, not the lowest dimensions for realizations of these groups. If one drops the linearity of the action, the dimensions are lower. And here is the proper start of my seminar. So the main motivation of my seminar is this thing. So about 20 years ago, I read a very nice article of Sigurdur Helgason, in which he writes the following. And now I will read it if I can. So I will read it because it might be. So what Helgason writes, Killing had been led to expect that G2 could be realized as a transformation group in R5, but not in a lower dimensional space. So Helgason even says stronger than I say, that the G2 cannot be realized in lower dimension than 5. And Helgason says that Engel and Cartan showed that it can be realized as the stability group of the system of such free Pfaffian forms in dimension 5. And moreover, Helgason says, Cartan represents F4 in the same manner by the Pfaffian system in R15, given by forms this one, so it's one form, and here are 6 one forms. So there is 7 one forms in dimension 15. So the annihilator of these 7 one forms at each point gives you an 8 plane. So actually what Helgason says here, that Cartan represents F4 as a symmetry group of a rank 8, certain rank 8 distribution in dimension 15. So in R15, at every point, there is an 8 plane defined by an as an annihilator of these 7 forms here, 7 one forms here, and this 8 plane going point by point give you rank 8 distribution in dimension 15. And if you look at the symmetry of this particular distribution, then what you get is the group F4 as symmetry. So this statement of Helgason made it clear to me how to realize F4. It is the symmetry group of a rank 8 distribution in R15. So this R15 is with coordinates xi, yj, z, zkl, where ij runs from 1 to 4, and this kl is smaller than k is smaller than l. So here is 4 plus 4 plus 1, so it is already 9 plus 6, so the dimension is 15. So these are the coordinates in this R15. In this R15, there is this 7 one forms, and then you look for the annihilator of this, you get a rank 8 distribution in dimension 15, and if you look at the symmetry of this distribution, it's precisely F4. So that's what Cartan did, and that's what Helgason writes in this story. And this realization of F4 is very similar to Cartan's and Engel realization of G2, where now in R5 he has 3 one forms, And these free one forms are the annihilator at each point of this R5 defines a two-plane. You have rank 2 distribution in dimension 5, and the symmetry of this rank 2 distribution in dimension 5 is realization of the group G2. So G2 and F4 are realized like this. And furthermore, Helgason continues. And now he says similar results for E6 in dimension 16, E7 in dimension 27, and E8 in dimension 29 as contract transformations are indicated in Cartan's thesis, actually in German version of Cartan's thesis. So Helgason says that similar realizations like those for G2 and F4, Cartan made also for E6, E7, E8, and these realizations are in dimension 16, 27, and 29. Then Helgason writes, unfortunately, detailed proofs of these remarkable representations of the exceptional groups do not seem to be available. Okay, that's what.
The symmetric group, did he have the symmetric group in mind?
Yes, yes. This is precisely this is essentially copied from Cartan, and this is copied from Cartan. Cartan precisely did it like this. But anyhow, Helgason says that there is E6 can be realized in dimension 16, E7 in 27, and E8 in 29. However, Cartan didn't say how to do it. Okay? And this is in, I like this paper very much. And this statement agrees with the, if I look at the German version of Cartan's PhD thesis, I just compared it very recently. This is what Helgason writes here with Cartan's thesis. Cartan wrote this thesis twice. First in German. First, his thesis was first published in German. Only next year it was published in French. So at this time, PhD students had to write two theses in two different languages. Anyhow, so if I just compared this very recently with the German version, and if I don't know German, but I just look at the very end, and I looked at the last three sentences. So the sentence last -2 says precisely this what Helgason says. Then in particular, we have the E6 in dimension 16, E7 in dimension 27, and finally E8 in dimension 29. That's what the sentence number n-2 in his thesis says. And then the sentence number n, so that's sentence n-2, and that's the sentence number n. And then he says that the five exceptional groups can be realized in no lower dimension than 14, which is G2. In lower dimension than 5, which is G2. In 15, there is 24. In 16, no, what I'm saying. In 5, what is G2? In 15, which is F4. In 16, what is E6? Now, in 27, what is E7? Which has wrong dimension, because E7 has dimension 133. And then eventually Cartan says 57 for E8. 57 for this group of dimension 248. So definitely 57 for E8 is in contradiction with 29 for E8, right? So he wrote two sentences. So as you see here, in these last three sentences, there are two misprints. There is misprint 29 here, and there is misprint 123. What Helgason took to his review paper, he just read this sentence and said, okay, E8 is realized in R29. If he read the last sentence, he would understand that E8 is realized in 57. And actually, Cartan explicitly writes that it cannot be lower than this dimension. And he says here 29. And for me, this Helgason story was the was the main source of my knowledge. And for years up to this year, I was believing that E8 can be realized in dimension 29, right?
But end of the German factor does not exist.
Yes, in lower dimensions. Yeah, so the last sentence has explicitly that the sentence last minus 2 is wrong, right? Or at least 2 of them are in contradiction. Okay, so conclusion number 1, Cartan's thesis in German has 2 misprints, and Helgason amplified one of these misprints in his influential review article, which made such an uneducated person like me to believe for many years that the lowest dimensional in which the exceptional Lie group is E8 is realized is 29. It's wrong. And Cartan is absolutely, what's going on? Why does it? And Cartan is absolutely innocent here. It was misprint in these German printers were simply wrong. And that Cartan was innocent is visible from his thesis in French. He writes explicitly in French that type E, there is rank 6, rank 7, rank 8, then it's about type F, so it is E6, E7, E8, there's F4 here, and there is G2, and he says that actually E6 of dimension 78 has 2 types of realizations in dimension 16, because it has this maximum subgroups of dimension 62, and he says that there is 1 realization of E7 in dimension 27. There is 1 realization of E8 in dimension 57. There are 2 realizations of F4 in dimension 15, and there are 2 different realizations of.
Does he write that the terminal dimension with 57?
He wrote this in German thesis 1 year before. You know, reading Cartan is a pain. So first of all, my knowledge of German is 0, and my knowledge of French is so. But even if I knew both of these languages perfectly, reading Cartan is difficult. And but one can read his theorems. It is why that's a lesson from a guy that sits on both stools of mathematics and physics, that if you pass from mathematics to physics, don't write your results just by words. Or if you have any result, display it always. And that's what Cartan did, and it's good, because what he writes is, delicately speaking, difficult to read, but he displays the result. And as I said, Cartan is innocent. He gave the proper lowest dimensions of realizations, and he actually have told, for example, that this E6 has 2 different realizations in dimension 16, and so Cartan, that's Cartan's thing.
So how many times did you wrong statement by Helga?
Many times. Okay, anyhow, so let me clean the mess of which I created, actually. I don't know if anybody else was reading this Helgason paper, but I did.
What about string people?
They are interested. Okay, that string people is another story. As I said, physicists usually are interested in representations, and not these are general relativists that really look for symmetry groups as transformation groups of manifolds, like symmetry groups of metric, right? Usually the particle physicists usually use only the representations, right? Anyhow, I don't know anything about particle physics. Let me go further. So let me clean the mess which I created, maybe. So recall that as far as the lowest dimensional faithful representations are concerned, we have G2 represented in the lowest dimension 7, F4 26, E6 in 27, E7 in 56, and E8 in 248. What Cartan says that actually G2 can be realized in dimension 5, F4 in dimension F4 in dimension 15, E6, 16, E7, 27. So you see there are much lower, these realizations, these non-linear realizations of these groups are in much more lower dimensions than the lowest dimensional irreducible representation. Yes.
Because I somehow feel confused, for some time. Well, I understand what is faithful representation, but I understood that, well, you were saying realization is just a transitive action. And, transitive action of the lowest dimension is just on one point. So it's 0. So what do you
No. I want
about the isotropy group?
No,
why do you distinguish between, realizations and just classifying closed subgroups? Because, if you have a closed subgroup, then you have a transitive action on the cosset space. So, so what's the point? From what viewpoint these are lowest dimensions? Because for me,
okay,
the
so
dimension is 0. Okay, thank you.
I understand. So the point is that for me, I would like to have some n-dimensional manifold with some structure for which a given group is a symmetry group. So that's what I mean by the realization of a group. I would like to realize a group as a transformation group on a manifold. And this transformation group, and if I ask myself when such a group can be realized, as you rightly said, and I also said it at the very beginning, one has to find the biggest closed Lie subgroup in this group. And you are right that to say what are the lowest dimensional realizations is to find the biggest dimensional, largest dimensional subgroups in a given group. That's correct. But what I want to say is that I'm just like giving an account on this, what people did more than 100 years ago and how they did it. So actually for these exceptional groups, it was absolutely, for a while, it was non-trivial to find these maximal subgroups. And that's what Cartan did. So that's what I'm just talking about. Anyhow, so what I stress is that these nonlinear actions of group on manifolds are in much lower dimension than the lowest dimensional representations. Okay, let's go. So if you would like to understand these numbers, there is a group, there is this club of people which are called parabolic people that do parabolic geometries, and they understand these numbers. So these numbers here, they understand these numbers. So my next step is just to try to tell you how they find these numbers, how you can find these numbers. Okay, so the numbers of the lowest dimensional realizations can be get from the Dynkin diagrams of simple Lie groups. And here are these diagrams. So these are diagrams for this A, B, C, D. In particular, these are diagrams for SO to Ls, right? And here are the Dynkin diagrams of this exceptional. So this diagram for E6, E7, E8, F4, and G2. And now the next step, which I have to tell you what they do, they know the following fact that every complex simple Lie algebra can be graded. That means to be decomposed onto a direct sum of vector spaces. So there is a Lie algebra, there is a complex simple Lie algebra G, and this can be graded, meaning that it can be decomposed onto such vector spaces, direct sum of such vector spaces, and these vector spaces are such in this Lie algebra that their commutator of Gi with Gj is in Gi plus j, and if I plus j is greater than this P then it is 0. So somehow there is every simple Lie algebra can be graded in such a way that it can be decomposed onto these spaces, and the decomposition is quite symmetric, meaning that every graded component of, let's say, I is of the same dimension of minus I. Okay, so this happens. This symmetric decomposition or this symmetric gradation is a characteristic feature of simple Lie algebras. That if you look for gradations of them, they will be just symmetric. Okay, and this part with minus is called G minus. This part with plus, this indices being positive is called G plus, and this which is in the middle is G0. Okay, so if you look at the commutation relations of these things, you see that the part G0 plus G plus, this thing, so every such gradation defines a subalgebra. So here there is a subalgebra P, which is from G0 to the end. No, because if you just make commutations, you will not go out from this because of this rule. So there is a subalgebra here, and this is called parabolic subalgebra in this simple Lie algebra. And also you can see that this thing here from G minus plus G0 is also a subalgebra, and it is also parabolic. It is called opposite parabolic to this one, and it is isomorphic to this P. Okay, so if you have a simple Lie algebra, you can grade it like this. And what is a parabolic subalgebra in a simple Lie algebra G? One can characterize it as a such subalgebra of G for which its orthogonal complement with respect to the Killing form is a nilpotent Lie algebra. Okay, that's the definition. It's not the definition, but you can use it as a definition if you want to know what is parabolic subalgebra. But I explained what is a parabolic subalgebra if you have a gradation. Okay, okay. In our settings, for example, this killing orthogonal to P is G plus, and killing orthogonal to P opposite is G minus. So in particular, G minus and G plus are nilpotent. And actually, this G minus is P step nilpotent, meaning that if you just make commutators of G minus 1 with first G minus 1, then you produce the next one, and so on and so on, and at a certain moment this terminates to 0. Okay, so that's what we know. What I want to tell you that simple complex simple Lie algebras can have is that you can just grade it, make gradation in them, and this gradation corresponds to a choice of parabolic subalgebra in G. Okay. So now there is the following fact I will be needing: the number of non-equivalent gradations in a simple Lie algebra. It turns out that a simple Lie algebra is a complex simple Lie algebra admits a number of gradations, and now you would like number of non-equivalent gradations. And now you may ask how many of these gradations a given simple Lie algebra has, and the fact is as follows: the number of non-equivalent gradations in simple Lie algebra is equal to the number of non-isomorphic parabolic subalgebras in G. And the nicest thing is people understood that if you look at the Dynkin diagram, so the number of gradations, or the number of making choice of parabolics, is precisely equal to the number of non-equivalent decorations of a Dynkin diagram of the simple Lie algebra by putting crosses on the nodes. Okay, so so if you want to know how many non-equivalent gradations a simple complex Lie algebra has, you just look at its Dynkin diagram and put randomly crosses on the nodes. And every such choice corresponds to a choice of parabolic, and it corresponds to a gradation. Okay, so that's the result which I will be using. So for example, here, what I mean by non-equivalent crossing. So I just took E6 and I made this cross, or I took E6 and I took 2 crosses, or to these 2 crosses, or these 2 crosses, or these 3 crosses. Each of these are these decoration with 1 cross, this decoration with 2 crosses, this decoration with 2 crosses, but it's non-equivalent to this one, because by what I mean by equivalence here, you make a group of motions, no, actually more, with reflections in the plane, and if you just can put the diagram on itself, then it means that it is equivalent gradation, equivalent decoration. Okay, so for example, this here I just put this decoration and this decoration is equivalent. So this corresponds to the same choice of parabolic or the same gradation. This is equivalent. This is equivalent. So if I make a reflection, and I didn't say that these are not all. I didn't say that. You can put as you can even count how many you can do here. I don't care, but I just want you to know that if you want to know how many gradations a given simple D algebra has, just put this, evaluate the number of putting non-equivalent. I don't care. Okay, let me go. You can count it yourself. Okay, so what each cross Dynkin, so here I do it on the example of E6, okay? So each cross Dynkin diagram corresponds to a particular choice of parabolic subalgebra P in G, and as such defines a gradation, because choice of parabolic is the same as just grading the algebra. And so in particular, you have split of this, there should be G here, not P. Gradation G equal G minus, G0, G plus, right? There should be G here. So what cross diagram visualize is actually the G0 part of the gradation. So if you have a Dynkin diagram, so you have simple D algebra, take its Dynkin diagram and make crossing. Some choice of crossing, for example, this one, right? And what this cross diagram visualizes, it visualizes what is really the G0 in this gradation. So choosing crosses means I choose a parabolic. Choosing parabolic makes me gradation. Gradation has G0, and actually what the cross diagram visualizes, it visualizes G0. It says that G0 is nothing but a direct sum of a simple part, which in this case would be just D4 plus 2 central elements. So actually, what cross diagram visualizes the G0 part of this gradation, it follows that G0 is a direct sum of the semi-simple part and the center, which is a direct sum of a number of C's. So G0 looks like the semi-simple part and the number of these things, and the semi-simple part is precisely this what remains with the diagram when you get rid of the crosses. So this is how this GSS looks, and the number of C's and how many numbers of C you have here is how many crosses you did put. So for example, in our first picture on the left, the gradation corresponding to this cross in E6 says that that G0 is actually having this part here, which is the diagram for D1, 2, 3, 4, for D5, right? So there is D5 here as semi-simple part plus 1C. So actually the G0 in this gradation chosen by this cross is essentially SO10 plus C. In the second case, we again have, now we have 2 crosses. And what remains after 2 crosses is just D4 here plus 2 C's. So this G0 is SO8 plus 2C. The next one is interesting because this semi-simple part is just this here, which is just SL4. This here, which is SL2. So it is SL4 plus SL2 plus 2 crosses plus 2 C's, and so on. Okay. So it is how you see what crossing means to your gradation. You simply will know what is G0. Okay. And this is very good to understand what is the dimension of parabolic related to this, and what is actually the dimension of homogeneous space G mod P, right? So, so now recall that G minus that this split in simple Lie algebras is symmetric. So G minus has the same dimension as G plus. So if we just make crossing, we make a gradation onto G minus, G0, and G plus, and then the dimension of G minus is the same as dimension of G plus. Dimension of G0 is some k, and we can see what is G0 knowing these crosses, so we can calculate dimensions. We can calculate dimension of, we know what is dimension of our starting Lie algebra, and by this, if we consider a pair of a simple Lie group with parabolic subgroup corresponding to this choice of your parabolic Lie algebra, then one can very easily see what is the dimension of the homogeneous space. It is just dimension of G minus dimension of P, and which is precisely dimension of G minus, which is S, and because 2S plus K is R, then S is equal like this. So you can calculate very quickly by putting crosses on the Dynkin diagram, you can calculate the dimension of the homogeneous space of your G mod P, right? And here is the story of Cartan, right? So if we just look at group G2, so if we look at group G2, it has dimension 14, and you can make either this cross on the Dynkin diagram or this cross. They are non-equivalent because here the cross goes from the arrow goes to the node, and here the arrow goes off the node, or the other way around. So there are two non-equivalent putting crosses on lateral thing. And if we just cross G2, then what remains is just A1, which is SL2, plus 1. So the dimension of SL2 is 3, plus this one is 4. So 14 minus 4 divided by 2. There is realization of G2 in dimension 5. There is another realization of G2 in dimension 5. There is realization of F4 in dimension 15, of F4 in dimension 15, and they are non-equivalent because this cross makes us G0 SO7, and this cross makes us G0 SP3, for example. So there are two non-equivalent realizations of F4 in dimension 15. Now, as for E6, if I make cross here or make cross here, that will be the same because they are equivalent. So there is only one, as Cartan says, realization of E6 in dimension 16. There is only one realization of E6 in the lowest dimension 27, because if I make this cross, the dimension will be 33. And there is one realization of E8 in dimension 57 if I take this cross. So it is how you get these numbers from Cartan, okay? And this is bread and butter for these parabolic people, as I call them, okay? Okay, so did I clear up the Helgason-Cartan story? So I recall one more sentence from Helgason. Similar results for E6 in 16 to E7, 27. E8 now we won't know that it's 57. As contact transformations are indicated, unfortunately, the type proofs of this remarkable representation of the exceptional groups do not seem to be available. So, well, Helgason speaks about realizations in Rn, so he means realizations of real forms of the simple exceptional Lie groups. I discussed complex simple exceptional Lie groups, and my realizations were in Cn. So actually, what I was showing you, that was realizations of complex groups in Cn, not in Rn, right? All my numerical dimensions were complex dimensions. My homogeneous spaces were portions of Cn and not of Rn. Okay. Fortunately, every complex simple Lie algebra has a real form called the split real form, for which all the statements about its complexification G are true when one replaces the words complex by the real. So actually, all these realizations that existed for the all these dimensions and all these realizations that Cartan is talking about complex ones in complex spaces can be also realized for the split real forms of these Lie algebras in the same dimensions, and the realization is essentially the same, because you simply forget about complex numbers and you just work with the real numbers, and that's how you get the real realizations of these split real forms. Eh?
Do you know anything about the other form?
That's what I'm talking about. I'm here to just tell you. Okay. So yes, there are realizations of the split real forms of the exceptionals in all the dimensions mentioned by Cartan in his thesis. And these are the lowest real dimensional realizations among all the real forms. So that's the first hint to your question, that if you now consider all the real forms, these realizations that come from the complex are the lowest dimensional. Okay. Cartan, so I also say that first of all, these realizations that they are talking about are about split real forms, right? Moreover, I am very unhappy with Helgason using the word similar, because they are not similar. They are not similar to those of F4 or G2. And as I say, Cartan realized F4 and its split real form, denoted by F1, as an automorphist group of a certain A distribution in dimension 15. Actually, it is bracket generating distribution, such that if you take the commutators of this distribution of vectors in this distribution with themselves, you produce the tangent space immediately. So this bracket generating two-step distribution. Take the commutators of the A distribution among themselves, and you produce entire tangent space. So this is called 8-15 distribution. So Cartan realized F4 as a symmetry group of this particular distribution in dimension 15. This can be realized on the nilpotent Lie group G minus. So if you take this particular gradation that corresponds to this on this F4, then if you take G minus in the corresponding gradation, then if you take the Lie group corresponding to this G minus, Lie group G minus, such that its Lie algebra is G minus, then on this 15-dimensional Lie group, there is very well defined, on this 15-dimensional nilpotent Lie group, there is well-defined A distribution, and which is precisely this Cartan distribution of symmetry F4. Okay, and as I said, that if you just look for the corresponding gradation, this gradation is two-step, namely G minus is graded from G minus 1 to G minus 2, and this essentially corresponds to this A distribution, and this if you commute this one with itself, you land here, and this gives you this 8-15 distribution on the corresponding nilpotent Lie group. So Cartan realization of the split real form F1 is a two-step parabolic geometry. Cartan is very explicit in describing his realization of the split real form F4, which I have just shown you. He just writes precisely this formulae that Helgason wrote. So he was very explicit how to realize F4. But then you look at how he realized E6, for example, in dimension 16, he says nothing. He simply says that you can realize this because there is this subalgebra, this parabolic subalgebra of a proper dimension that makes the dimension of the homogeneous space 16. But he says nothing what kind of geometric structure is on this 16-dimensional manifold. But it turns out that this 16-dimensional manifold has no any kind of distribution. Actually, this E6 is a symmetry group of a spin, actually spin 5, R spin 5 structure on the tangent space. So actually you have a 16-dimensional manifold now, and on this 16-dimensional manifold, you have a spin structure, but actually this spin 5 structure in the tangent space, and it's R spin structure. So it is spin times R. Okay, and it is very different because this realization of E6 in dimension 16 as parabolic geometry is not two-step graded, but one-step graded. There is no any subdistribution in the tangent space whose symmetry is E6 as before, But there is some additional structure, which is this spin structure, whose symmetry is E6. Okay, so it's very different, and it's why I don't like that Helgason writes similar realizations are for E6, E7, E8. They are not similar to F4, to realization of F4 and G2. Okay, so Helgason's statement similar results for E6 are indicated in Cartan is again wrong. Realizations are not similar. In the same way, Cartan's realizations of split real forms E7, E8 are not similar to his realizations. So now let me ask the questions. Do I have some time more? How long I can talk? 15 minutes. Okay. So let me ask the questions. So I want to ask now the questions about the realizations of these split real forms of EL, similar, really similar to Cartan's realization of F4 and G2. Because as I said, his realizations in the lowest dimensions are not similar because they are one-step graded and not two-step graded. There is no distribution, right? So by this, I mean realization of these real groups as symmetry groups of a bracket generating two-step distribution on the manifold. So that's the question. Can I realize these guys as symmetry of bracket generating two-step distribution, right? And the second question is the following: true or not? All real forms of a given simple exceptional Lie algebra have the lowest dimensional realization in the same dimension. Or maybe if I just consider, for example, if you just look at E6, it turns out that it has a number of real forms. And now Cartan says that the lowest dimensional realization is in dimension 16, but he speaks about split real form. But what if I take some other form? Can these be also realized in dimension 16? So that's the second question. Are all of them have lowest dimensional realization in the same dimension? Of course, all of them except compact one, which doesn't have parabolic. Okay, so these are two questions. And let me go. So now we have to know something about real forms. And we know about real forms of group SO or SU even, but what are the real forms of this exceptional? So to enumerate non-equivalent real forms of a given complex simple Lie algebra, one decorates, but differently, its Dynkin diagram. And this new decoration is as follows. So one decorates its Dynkin diagram by, number one, changing color of some nodes from white to black, and two, connecting some nodes by arrows. So you take a Dynkin diagram, which is just with all nodes white, and you put some of these nodes black and connect some nodes by arrows. Okay, that's not so simple, but that's the first approximation how you do it. Okay, the rules as to which nodes could be changed into black and which nodes could be connected by arrows are too complicated to be presented here, so they put it away. I only mentioned that in the real case, the Dynkin diagram nodes representing simple roots of the Lie algebra can be either real, and if then you leave them on the diagram as white, or imaginary called compact, and these which are these nodes that correspond to simple roots which are compact, you make them into black, and they could be such that the nodes corresponds to simple roots that are complex conjugated. If they are complex conjugated, they are connected by an arrow. Okay, so there are three times of simple roots that could be in this real Lie algebra, and you denote on the diagram that those that are compact you put into black, and those that are complex conjugated then you connect them by arrow. And if you do something like this for a given Dynkin diagram, you get new diagram which is called Satake diagram, and this Satake diagram that corresponds to a given real form of this simple Lie algebra, now real one. Okay, so as I said, it's too complicated to tell you how to put this black into whites, but for E6, there are 5 real forms. There is the compact one in which all the nodes are black, and this one doesn't have any parabolic, so we don't care about these ones. And there are these ones. There are E1, E2, E3, E4, and this is the split one. So the diagram of the split one is precisely as the diagram of complex ones. That's what I said. That everything what I said about complex, you can say about split real form. But there are three others. There are guys that this node is complex conjugated to that, this node that's complex conjugated to that. These are reals, or there are three compact guys here. They are complex conjugated, and one is real here. Okay, so that's all like this. So there is real. So there are four real forms which have parabolics, right? So if you are asked how many real forms E6 has, it has 5, right? And these are the corresponding Satake diagrams. Okay. So now how we choose parabolics? Take Satake diagrams and decorate it with crosses. But now, of course, you have some selection rules. You cannot do it blindly. So choices of parabolics in one of the real forms is just to put crosses on the Satake diagrams as before, but now we have selection rules. It is forbidden to cross black nodes. So if you have Satake diagram, you cannot cross the black ones. And if you cross a guy that is connected by arrow to the other, so it is this guy you cross, so you have to cross this one because it's complex conjugate, right? So there are some kind on the complex thinking diagram, you could just put crosses as you want, and here you have to obey these rules that you cannot cross black ones, and if you kill the complex one, you have to kill the complex conjugate. Okay. And the rules, what the cross diagram represents, it again represents G0. So the story is the same. The only thing is that now we have these selection rules of putting the crosses. Okay. So now, so for example, what Cartan did for E6, he crossed this route, and what remains was this here, which is 1, 2, 3, 4, 5, D5, which is SO10 plus 1. So it is, he finds this 16-dimensional realization of this Lie algebra. But we see that E2, E3, we will have not such 16-dimensional realization, because if I cross this node as Cartan did, I have to cross this one, right? And therefore the realization of this real form in dimension 16 is impossible in the way as Cartan did. It is possible when I just cross this one with this run, and then the dimension is 24. It is possible in dimension 24, but it's not possible in dimension 16. Actually, it's also possible in dimension 21 when I cross this one, but I don't want to talk about that one. Okay, so that's because of the second of the selection rules, we see that if we cross node lambda 1 in E2 or E3, we must also cross the node lambda 5 on these diagrams. Thus, the 16-dimensional realization of E2, E3, similar to the 16-dimensional realization of E1, is not possible. There exists, however, a 16-dimensional realization of E4. Here I can do it because this is not connected. And so this one can be realized in dimension 16, this one in dimension 16, but these two cannot be realized in dimension 16. Actually, the lowest dimension in which these two can be realized is 21. Corresponding to this cross here. Of course, there is a CR structure. That's how I got all of this. Yes. Yes. So let me now tell about this, what Armand is asking. So, s'il vous plaît. Accidental CR structures. I call them accidental. Oui, bien sûr. Accidental, which Joël Merker says that is crazy because accident in French is a very pejorative name. We cannot call it accidental. But it's not in English, so we pacified it. Okay, anyhow. wanting to be as close as possible to Cartan's realization of E1 when he crossed this node, we just crossed this node on E2 and E3, which means that we immediately had to cross these ones. And so with Denny and Joel and Zhao, we crossed node lambda 1 in E2, E3, and this by the second selection rule for us to cross node lambda 5. So what we got two E6 homogeneous 24-dimensional manifolds, E2 by corresponding parabolic and E3 by corresponding parabolic. It turns out that each of these real manifolds, this 24-dimensional manifold, this one or this one, has now 16 distribution, which is again bracket generating and two steps. So there is a 16 distribution that when you just bracket generate, you will produce 24 manifolds. And so this is really very similar to this what Cartan did. Now we have 1624 distribution whose symmetry is E6 by my construction, because it's naturally there. So it is homogeneous, E6 homogeneous, actually E2 or E3 homogeneous. So this is really the realization similar to Cartan's realization of E6 in dimension of F4 and of G2. This is the lowest dimensional, I believe, realization like this of these E's. Okay. So we have a realization of an exceptional, in this case E2 or E3, which is similar to Cartan's realization of F1 as two-step parabolic geometry and how the group is realized. It is a symmetry of this distribution. But actually, if one looks at this distribution, there is something more. This structure is that rich that that on this distribution is naturally defined a complex structure, integrable complex structure from the distribution to this distribution, which is compatible with this E6 symmetry. Again, is given by construction. So actually what we have here, we have in this way, we constructed two CR structures of codimension 8 in dimension 24. So we have a 16-dimensional complex plane at every point embedded in real 24. And so in this way, we actually constructed a CR structure of CR codimension of CR dimension 8 and real codimension 8, which can be easily embedded in C16. And it has E2 and E3 symmetry. And as I said, we call these structures, these CR structures, accidental, because actually already the distribution has E6 symmetry. This J is just like for free. So if you look at the symmetry of the distribution itself, it is E6, but moreover, there is E6 compatible J there, which makes it into CR structure. And it is why we say, okay, this symmetry is a symmetry of a distribution, real object, but actually it is the same symmetry as a certain CR structure, right? It is why we call these CR structures accidental. Okay. And what if we if we take E1 and E4 and we do the same? What if I just do it here, not like Cartan, only one node, but this one, and this, then what you see, we also get 24-dimensional E1 or E4 homogeneous manifold, and with 1624 distribution. But now this distribution has no J in it, but K, such that K square is identity. So it is now what we have, it is E6 symmetry para-CR. These are called para-CR structures and accidental para-CR structures. Okay. So, but here the situation is quite interesting, because this K, there we had 16-dimensional real distribution and J in it. J, as a complex structure, the square is minus identity, its eigenspaces are complex, right? Because the eigenvalue is plus minus one of this J on this 16-dimensional space. But here we have K, so here our distribution, which is 16 distribution in dimension 24, because of this K, splits onto two integrable subdistributions of dimension 8. So actually I have my 16 distribution, which actually splits into two 8 distributions, the commutator of this A distribution produces guy, which is now again 8-dimensional. And we have almost the diagram of D4. And of course, we do have it, because if we cross these 2 points or these 2 points, the semi-simple part or simple part of this diagram is D4, which is the group SO44 in real terms. So it is either this one for E4 or this one for E1, right? So somehow we see that in this our para-CR structure, we have this 16-dimensional distribution, and we have this commutator that's entire tangent space. But if we look at the G0, which acts on the 16 distribution, this G0 thing is SO8 or SO44, right? And if you look at all the Dynkin diagrams, let's talk about complex ones. If you look at all Dynkin diagrams at their symmetry, they are just like, they have dual symmetry. The highest possible symmetry is Z2, except of one diagram for D4, which has Z3 symmetry. And this Z3 symmetry, Cartan was very interested about this, because this Z3 symmetry of this Dynkin diagram, although perhaps Cartan didn't know about Dynkin diagrams, this Z3 symmetry of Dynkin diagram must mean something. And it means something very peculiar about representation of group SO8 and representation of group SO44. Both of these groups have 3 real, irreducible, non-equivalent representations of dimension 8. There is standard representation, the defining representation of SO8 in dimension 8, but there are 2 others, and these are spin representations. And this is called, by Cartan, this is called triality. Group D4, complex one, or group SO8 or group SO44 has 3 non-equivalent irreducible representations in dimension 8. One of them is standard representation, and 2 others are spinorial representations. So it's only dimension when group SO has 3 inequivalent representations in the same dimension as the group is defined as the defining representation. And so this is called, by Cartan, is called triality. So as I said, if we cross these things, meaning if I have this my para-CR structure of type E4 or E1, then the G0 there is SO80, SO44. Both of these real algebras share the phenomenon of triality. They both have 3 real non-equivalent irreducible representations in dimension 8. 2 of these representations, say gamma plus, gamma minus, are spinorial in the respective 8-dimensional space of Weil spinors, S plus and minus. They are coming from the real 16-dimensional representation gamma, which is in the space of Dirac spinors. So the third representation is a standard vectorial representation in dimension 8 in the space of vectors. And if we just make this choice of parabolics in E1 and E4, then we get the split of this E1 into E4 into G0, which is my D4 plus these 2 guys, G0, and this G0 acts naturally on G minus 1, which is of dimension 16, and acts naturally on G minus 2 of dimension 8. And this G minus 1, because of this K that I told you, splits onto 2 8-dimensional subspaces. And actually, G0 acts on G minus 1 reducibly. It is 16-dimensional representation. So G0 acting on G minus 1 is a Dirac spinor representation in G minus 1. But this representation splits into 2 8-dimensional representations, which is just Weil spinor representations. They are non-equivalent, and G0 acts in G minus 2 as a vectorial representation. So this particular parabolic geometry is realization of Cartan's triality the action of G0 on these free spaces is in free non-equivalent representation of SO8 or SO44. So somehow this, what I have said here, these two para-CR structures here are geometric realization of Cartan's triality, and that's what I wanted to say. This is very like I was hand waving, but I can prove all these statements here and give you explicit representations and everything. I can write the same kind of formulae like Cartan wrote, but I didn't want to do it. Thank you very much. That's it.
Questions?
Say it again.
There must be some curve analog.
Ah, very good. No. These geometries are rigid. If you just, as parabolic geometries, they are rigid. They don't allow deformation. So they are really like, if you want, they are jewels kind of. So this CR structure, this accidental CR structure with these two accidental CR structures with various E6 asymmetries are parabolic geometries. They are flat models for a certain parabolic geometry, but this parabolic geometry is rigid, namely it doesn't allow a deformation to another parabolic geometry of the same kind. They are rigid. So they are really like jewels. If you want to have a jewel, it should be just particular. You cannot deform it.
So those here structures are how many dimensions?
With CR structure, that means these one is symmetry 6, they are of dimension 24. They are 24 dimension. It is real one for the dimension 24. There is a rank distribution and there is J. So they are of dimension 8. And then, but they can be embedded very easily. I can give you a formula how to embed them as CR manifold as the real submanifold in TCC. Because for dimension is 8, so we can. These are not hybrid surfaces. Any what? They are actually don't know.
So maybe I don't know so I know the people that need to match all of dimensions. So the odd dimensions, I haven't seen any odd numbers. They are all even numbers.
You are out of date.
Right.
Okay. Let me tell you. So to be very much out of date, let's go to Poincaré. So the concept of CR structure comes from Poincaré. What he was looking for, he observed that if you take a curve, a real curve in T1, and you take another curve in T1, there is always local biomorphism between T1 and T2, right? So here's a real submanifold of dimension 1 in the complex manifold of dimension 1. What Cartan did, he said, okay, I will take C2 and I will close to Poincaré. So I have real submanifold of dimension 1. But who prevents you of taking real submanifold of dimension of higher? I think so this CR structure, so the notion of CR structure comes from a structure that a real submanifold acquires from the ambient component. And what is the dimension of the real submanifold? Yeah. But in this case, they are 2 dimensions. 8. So they are in C16 of real dimension 24. So the real dimension of C16 is 32, and there is 24 dimensional submanifold, and on this 24 dimensional submanifold there is 16 dimensional field. And this 16 dimensional field has J on it, which is bad because J squares minus identity, but if I take another different form, this real form, I have RSPR field. So in R 16 plus R16, I take a 20, 10, 20, 40 multiple manifold, then it gets a 2 rank A distribution, and commutator of this rank A distribution gives me something A distribution A, and there is 3 different representations of S of A, let's say, are from distribution.
And those
So at every moment, at every point, we have realization of triality.
intervals here attractive is defined from
They are highly codimensional. So Levy form is not one Levy form, but a number of Levy forms. So there's a rank of Levy
I'm sorry, perhaps you didn't hear the questions, but is somebody else asking question? No, so thank you again. Panowie, jak chcecie zadawać pytania, to poczekajcie na ten mikrofon.